Hello and welcome everyone. In the previous video, we looked at the one-dimensional heat equation with these initial and boundary conditions, and we tried to solve it using an explicit finite difference scheme. Here, alpha is equal to delta t over delta x squared, and delta t is chosen based on the stability criterion, which is that delta t must be less than or equal to zero point 0.5 delta x squared. The stencil in this scheme tells us that the value at the current time step depends explicitly on the previous time step values. One of the key drawbacks of this approach is that it is conditionally stable. That is, we need to select a smaller dx to approximate the derivatives accurately using the finite differences. And the stability criterion suggests that dt must be even smaller, which means many more steps will be required for a given total simulation time. To obtain an unconditionally stable method, we can use the backward time difference and get the implicit backward time central space difference formula. Alpha here has the same definition as in the explicit solution. The stencil now shows that to calculate the future time step values, we also need to use the unknown values at future time steps as well, therefore requiring a simultaneous solution. We can write this in the matrix form Ax is equal to B. Here A is a tridiagonal matrix which is diagonally dominant, and we can use one of the methods we discussed in the previous videos, such as Kraut's LU decomposition, to solve the system of equation for each time step. In the previous video, we got this explicit finite difference solution of the heat equation. In this sim, we used dx equal to 0.01 and dt was set equal to 0.5 dx squared. For the implicit BTCS solution, we can update our Python program. As we saw before, we create the tridiagonal matrix A and then solve the system of equations for temperature at each time step. The solution obtained using the implicit BTCS method and with the same dx and dt values as in the explicit finite difference solution is the same. However, one advantage of using an unconditionally stable method is that we can also use coarser time sampling and still be able to get the solution. Here we have used dt is equal to 0.01, which is much higher than the value used in the explicit finite difference scheme. With this, we conclude our video. I hope you liked it. Please subscribe to my channel and thanks for watching.